First of all, thank you to the organisers for the invitation, and thank you to you for staying. I am conscious that the icebreaker starts in less than 5 minutes, so please excuse me if I start talking faster and faster as that very real deadline approaches. So I'm going to talk about sound mapping. First of all, well, both in a European context and also in a more global context with respect to the International Quiet Ocean experiment. So all the work I'm talking about here comes from an increasing societal concern about the impact of anthropogenic underwater sound, underwater noise, on marine life. And this noise comes from a wide variety of sources. Shipping is one of the more obvious ones. Oil and gas exploration, where air guns are used to make noises in the ocean, and then they listen for echoes from gas and oil-bearing strata beneath the seabed. But there are also sources of sound which might be associated with more environmentally friendly, ecological sources, like the wind turbines that I show here. There's a big investment in offshore wind power in Europe at the moment, but the columns on which these turbines are mounted are effectively hammered into the seafloor. And during this pile driving process, noise is generated, obviously, because you're hitting a large metal column. It propagates away from the location of the wind farm, and there's a potential that it may raise the sound level in the ocean. Now, if the sound level in the ocean due to anthropogenic activities is increasing, and that is an area of research, I should say, but if it is increasing, there's the potential that it may have a negative pressure on marine life. All sorts of marine life use sound, everything from crustaceans at one end to large baleen whales at the other end, with fish and porpoises in the middle. And they use it to communicate, to navigate, to find food, to find mates. Everything you need to do to have a successful, healthy, reproductive life may have an acoustic component to it. So if there's noise in the ocean being generated, it may have a negative pressure that will cause reductions in the populations. That's where the societal concern comes from. And in a global sense, this has led to the International Quiet Ocean experiment. And on the more European context, there's now a requirement for the monitoring of sound transmitted during seagoing industrial activities. And that's part of the Marine Strategy Framework Directive, which has already been mentioned in a previous presentation today. Starting off with the global picture, the International Quiet Ocean experiment was conceived a few years back, and originally the idea was that this would be an experiment that would last a single day. And during that day, all sources of man-made sound in the ocean would be turned off, and experiments would be performed to see what the effect was on the marine environment. Now, the paper which is referenced here discussed that and looked at the possibility of doing it, and they came up with an estimate that the cost of doing that, one day's quietness in the ocean, to the global economy would cost about $10 billion. And that was considered to be a little higher than the budget that was available for the experiment, and so a new plan was needed. And what we have now is a science plan, and this science plan provides a framework underneath which research projects can be carried out, organised according to the themes that you see here. And I'll talk a little about the ocean soundscapes theme. A soundscape is kind of the hearing version of a landscape. A landscape is how an environment looks, a soundscape is how it sounds. And this is used in ecology, in airborne sound, where you talk about the soundscape of a city or the soundscape of a marine or of a national park. And it's beginning to be used in underwater acoustics as well. And one of the pieces of work that's been done under the International Quiet Ocean experiment was done by Professor Doug Cato at the University of Sydney. And what we have here is a map of the shipping distribution in the ocean. This is a global average data set showing you where the ships are, and you can see they follow reasonably predictable patterns. The lines that you see on the map are great circle routes between various busy ports and choke points like the Suez Canal and the Panama Canal. And the red areas show you places where there's intense shipping activity, and that's associated with industrialized areas, the eastern and western seaboard of the US, European waters, and Asia around China and Japan. And what Dr. Cato did was to take the information from around the coastal waters of Australia and turn it into a noise map to predict the traffic noise at 50 hertz. Down at this low frequency, 50 hertz, shipping noise is an important component of the sound in the sea. And as you can see, the map that he's produced is associated with these tracks here. This is the Great Circle route to the Suez Canal. This one's taking you to the Persian Gulf. And the highest levels of noise are over here on the eastern seaboard of Australia, where most of the large cities are, and there's most marine traffic. So this is an example of trying to predict what the ocean soundscape is affected by, in this case, shipping. On the European side, we now have monitoring guidance, which has been produced by the European Commission. This is the executive summary describing it. And this sets out several indicators about how you would go about monitoring and measuring the anthropogenic sound. And as an example here, indicator 1121 so it looks at trends in the annual average squared sound pressure. That's effectively one measure of how loud it is underwater. Measured in two low-frequency bands, 63 and 125 hertz, and either measured directly or inferred from a model. Now, there's a specific reference to models here, because if you were to try and monitor all the European waters directly with a measurement program, that would become very expensive. At-sea acoustic experiments are difficult to do. You either have to go out there and deploy the equipment. The equipment needs to be very strong to survive for a long time in the harsh marine environment. Then you have to go back and get it. Or alternatively, you find yourself laying tens of kilometres or even hundreds of kilometres of cables to produce a constantly monitored system. So a more cost-effective solution is to have a modelling approach where you're predicting the sound field in the ocean, and then to have very well-directed series of measurements at well-chosen sites to constrain that modelling activity. And so this is why we have this mention here specifically of modelling and measurements. So this is some work that my colleagues at TNO have done. At TNO we have an interest in underwater sound, and we've got the capability to do mathematical modelling and prediction of it. And what we have over here is a shipping distribution map, in this case not from the averaged geographic data set that I showed before. This is from AIS. This is the Automatic Identification System. It's a series of radio beacons that you can have installed on ships, and it transmits the ship name, its position, its course and speed. Lots of information which is necessary for us to predict the sound level that's going to be generated by that ship. Obviously, you're going to get different levels of sound from a very large container vessel than you are from a ferry. And you can see again how these things are concentrated in very organised lines for shipping lanes. And we also have hotspots associated either with fishing grounds or with marine wind farms if they're being installed, or offshore oil and gas platforms. And over here we have a prediction where all this information has been turned into source levels, and then the way in which that sound travels from those sources through the environment has been used to predict the noise level at each location here. And this is the broadband SPL. SPL is sound pressure level. This is another measure of effectively how loud things are underwater. And broadband in this case means across all frequencies. So you can see what's going on here. The patterns that you see here are very strongly correlated with the patterns that you see over there. And the closer you are to a shipping lane or a hotspot where there's some local activity, the louder things are going to be. This is the broadband level. If you're interested in how this sound is going to affect marine life, you need to take account of the fact that different species of animal are sensitive to different sounds. Some animals are sensitive at low frequencies, others at high. So you need to weight, I just knew it was going to do that. So you need to weight it by the audiogram. And this is the audiogram of one particular species, a porpoise. And so what you're seeing now is kind of the porpoise's eye view of the sound field. Patterns are similar, but the levels are the same. Excuse me, it's gone into automatic. So you can see how the porpoise is going to sense this sound on the basis of its audiogram. It's going to be sensitive to different frequencies to different levels. So we're involved here in an exercise in modelling sound, and we're doing mathematical calculations of underwater sound pressure as a function of time, space and frequency. In terms of time, we've got a variation of a wide different set of scales. Some things will change according to the time of year, others according to whether it's day or night. In terms of space, we want to look at North Atlantic, North Sea, anywhere where there's an interest in this work. And for the International Quiet Oceans experiment, that's completely global. In terms of frequency, we have to go from low frequency, where shipping noise is one of the more important ones, up to high frequencies where echo sounders, specialist sonars, are used to map the sea floor. They can be very intense at short ranges, but the sound doesn't travel very far because it's high frequency. And we also have broadband sound coming out from explosions. There are a lot of explosions in the ocean, particularly in the North Sea. In the North Sea, they're often associated with the disposal of bombs from World War II that were dumped in the sea by returning aircraft. And when you have an explosion in the sea, that's a very broadband signal. It contributes to the sound over a wide range of frequencies. And so to do this, we need descriptions of all the important sources of sound. Where are the ships? Where are the seismic surveys going on? Where are the pile driving? And we also need a lot of environmental information. Hence my interest in today's proceedings. And the reason you need a lot of environmental information is that sound can travel a long way underwater. This map here is from an oceanic engineering paper, and it concerns the detection of signals of explosions that took place off the coast of Japan. And these explosions were caused by the detonation of 40 kilograms of TNT. Now, you wouldn't want to be close to 40 kilograms of TNT when it goes off, but compared to a World War II bomb, this is a relatively small explosion. But nonetheless, the signals from those explosions were detected over here in the Juan Fernandez archipelago off the coast of Chile, 16,300 kilometers away. So, sound travels a long way underwater, so if you're interested in predicting the sound level at a location, you don't just need the sources close to that location and the environmental conditions at that location. You need this distribution of sources over a wide area and the environmental information all the way through that area as well. So we're quite data hungry in our application here. This goes back to some of the data that Hague was showing earlier on. Our existing set of data is based on World Ocean Atlas and the ETOP bathymetry data. And these are good databases. They're global, but they're quite... the resolution is now getting to the stage where we're beginning to wish that we had a little bit more. What I've got here is bathymetry from the ETOP database. We're actually quite happy with this. This is global coverage. It's got reasonable resolution and precision. This is the coast of Florida. I've chosen this area for a reason that will become clear in a moment. And you can see here, we've got a pretty good map of the bathymetry going from shallow here out into the deep. This is okay. We're also interested in finding out currents, and we've seen lots of very impressive simulations of, and indeed data of currents today. I'm almost embarrassed to show this. What we've got here is simply a map of the M2 semidiurnal component amplitude. So this is giving us average values for the north, south, east, west components, but it's time invariant, and it's certainly not a nowcast or a forecast of water flow. So here we've got a situation where we could do with some more information over and above what we've currently got. In terms of the temperature and salinity in the water, this is a map of the stratification. This is interesting from what Kurt was saying before for calculating the possibility of the presence of internal waves. And you can see red here is areas of high stratification, blue is lower, but what you can mainly see are these big blocks here. The World Ocean Atlas, very good database, but it's got one profile per degree per month. So this is getting to the stage now where we're reasonably certain that there were better, more precise, higher resolution data sets out there, and it will be useful for us to begin looking at using those for our noise mapping calculations. So if we need better predictions, we're going to need better input data, beyond the long-term averages that we've been looking at so far. We'll be interested in looking at temporal variations of the source distribution, if we can get some more information about the location of ships and marine seismic surveys. That's going to add to the quality of our predictions. We're also going to need temporal variations in environmental conditions, so currents, wind wave swell, ocean weather, and we'd like to be able to do hindcast, nowcast and forecast, all directions in time. So what I've been doing recently, I come here not so much as a user of the CMEMS data set, as a prospective user, a new user. I've downloaded some data, looked at it, thought, this looks really good, we must use it. And so just as an example here, this is the reason I chose the coast of Florida here. You can see the Gulf Stream running up here. The colours are giving you the amplitude of the water flow, and the arrows giving you the direction as well. So this is very much an advance of what we had before, which was just that simple M2 tidal component. There's also temperature change associated with the Gulf Stream. We see this warm water here running up the coast of the US. Up here we've got northerly waters, which are considerably colder. Now, across this boundary here, the temperature changes quite considerably. The sound speed is changed by that change in temperature, and so the sound is going to refract as it goes through that. The sound won't travel in straight lines, it will be bent just as light is bent by a set of spectacles. And we need to include that refraction in our models, particularly because it can critically control the interaction of sound with the seabed. If you have a particular shape of sound speed profile, it can bend the sound down into the seabed, and if the seabed is absorbing, that's the last you'll ever hear of that sound. So you can get a combination of conditions that, because of features like this, that make the sound propagation very much poorer than it otherwise would be. And that, of course, can change with time as well. Similar patterns on the salinity. This is salinity in parts per thousand. We've got the colder water in the north is fresher, or lower salinity anyway. I wouldn't go so far as to say that it's fresh. But we've got a salinity front here as well as a temperature front, and that again is going to have an effect on the sound speed. So in terms of additional requirements, we still have sources of significant uncertainty in our modelling capability. And the big one is associated with the seabed properties. We need a geoacoustic description or a geotechnical description of the seabed so that we can calculate the reflectivity, the acoustic reflectivity. If the seabed is made of a hard rock, it's going to be quite reflective and the sound will travel a long way. If it's made of a soft, absorbing mud, any sound that hits it will be taken away and we'll get a lower noise level on average. So that's something that we still don't know particularly well. We'd also like to get some shipping distribution that goes beyond the AIS system. AIS isn't compulsory. I think in European waters it is for ships of a certain size, but it's not compulsory for all ships. And some small ships can make an awful lot of noise. So there are ships out there which